recording is rolling. Welcome to Tuesday, December 7th. I have a rotational inertia lab lined up for you guys. Now, this is going to take a couple of days, so I'm going to take about the first 15 minutes or so of class to walk you guys through exactly how this works, what I'm looking for, because it has a bunch of little parts. Hey, guys, everybody focus here. Right, there's a lot of little parts to this lab, and I want to make sure everybody knows what's going on with this thing. Right, so you guys see some PVC pipe setups back there, has this T shape. Now, those can rotate about this vertical central axis, sort of like you see here. Let me show you the mechanics of what this is, and then afterwards I'll show you what you're trying to find. Right, so there's a string that's wound around the central pipe, and you can loop that around one of these pulleys that has very small mass, so let's treat this mass as negligible. And then hang a lab mass over the end. Now, if you release this from rest, is the lab mass going to fall down? Yeah. Is it going to fall down faster and faster? Like, is it going to accelerate? Yes, it will, because there's a net force on it that's driving it. Net force means there's going to be an acceleration. F equals ma. Okay. Which I'll get back to that too. But let's say what's going on at the other end of the string is that this is tied around the central axis. Isn't that going to cause this thing to rotate, like spin? Right? Hey, do you guys think that the linear acceleration of this mass falling and the angular acceleration of the speeding of spinning are related to each other? Right? I mean, they'd have to be, right? Would it have something to do with the radial size of the central pipe? Right? Let's get a close-in shot of that. So zoomed in here. Right, I'm just coloring the pulley red because you guys know those pulleys red, but not because it's especially important or anything. But right, yeah, here's the central pipe. Right, it's going to be spinning around this here central axis, and the radial size of this thing is important because that's what's going to connect the linear acceleration of the mass going down to the angular acceleration of the spinning. Also goes through torque, because you guys can imagine that isn't there going to be some tension in the string, and doesn't that tension act at this radial arm distance? Like this R across this force, R cross F, that would create a torque that would cause this thing to speed up in the first place, wouldn't it? Okay. But the other form of reversing was this right here. So the linear acceleration of the lab mass falling and the angular acceleration of that PVC pipe spinning. Okay. So get this connection. Because I had some questions before. So what R does this refer to? So on the lab page that I go through, there's a table that R does refer to the radius of the central pipe, okay, which is probably really close to a centimeter. Okay, probably about a centimeter. Is that case, right? Now, let's think if you were to play around with the system. I haven't even quite gotten to what I want you guys to solve for yet, but just thinking if you were to play around with some stuff, how would that affect the motion of this? Like, for example, you could very easily pop these T-arms off this PVC pipe. In fact, if you want to try this when you get back there, you can do that. You can pop off these arms, just have like a vertical pipe. If you do that, then how's this lab mass going to fall? Really fast or really slow? If you get rid of these arms, really fast, isn't it? No, it'll accelerate. It's going to like really fast. This thing will spin. But when you attach these arms here, it's not going to slow down the process, right? You know what else I bet you could do to slow down the process even more if you wanted to? If you ever wanted to like tweak this lab or put your own variables in and extend this a little bit beyond exactly what I have them, go for it. For example, you might want to do something like maybe take some additional lab masses at the end here. Do you think that would slow down this process even more? Yeah, because effectively you're adding more inertia to the system, aren't you? Like inertia. And that's where this lab is going. That's the question I want you guys to figure out is, what is the rotational inertia of this T-shaped PVC pipe about this vertical axis? And you do have to specify what axis it's spinning around, because if you pick a different axis to spin around, then the rotational inertia would be different. But what is the rotational inertia about this vertical axis? Okay. Now, how could you figure that out? Well, it has something to do with the motion of the linear motion of this lab mass, has something to do with torque, has something. Where are we going to go with this? So let's get to this page that's on your desk. Now, you guys have a full page that looks like this. If you see the half-page version of this, ignore that. That's for my honors classes. But you guys are going to have a front and back. Oh, whoops. No. Sorry, got this one. Okay. You guys, front and back. It's going to look like this. So I'm going to have you guys do an AP-style write-up with this. Of course, won't do this on every lab, but the ones that I think that you can get something out of, or that would be pretty good for AP style. Over the weekend, I went home and did this myself and create a scoring rubric. Now, this lab's going to take a couple of days. So tomorrow, I will go over, say, an answer key with this and have you guys score yourselves out of 12 points. So you guys know the classic 5 parts. What question are you trying to figure out? What are the relevant measuring tools? What's your procedure to gather the data? How do you analyze that data? Say, once you have it, how do you crunch it? This might involve equations. This might involve graphs. Okay. Then finally, conclusion. And when I reiterate this point, make sure that your conclusion actually answers your question. Whatever your question is, make sure your conclusion is consistent with answering that. Okay, okay, so you guys remember all that. Let's take a close look at what I've got in this table. I'll show you guys my thought process going through to help you answer this. Okay, just go from beginning to end, and this should make sense by now. Okay, so let's get some numbers on the table. Like, hey, what's the radius of? Hold on. Pause. Let me backtrack a little bit. Because before I show you guys what the thought process is that I'm going to have you guys go through to actually figure out what is the rotational inertia of the system, I want to go down a little side quest to think what's an alternate way that I'm not having you guys do it, but maybe you could do a quick calculation and for comparison. So rotational inertia, you guys have a table of values in your book on page 257. One of them actually looks really similar to your lab setup, and that's this one right here. See this? Hey, that looks like that cross T on the PVC pipe maybe spinning around, and the vertical part of the pipe itself is not adding very much rotational inertia, but the arms are adding like a lot of rotational inertia. So if you wanted to simplify it and assume that maybe use this as a model for that, what you could do is you could say, hey, what's the total mass of these arms? Pop that in for this M. Figure out what's the total length from end to end, call that L, and you have 1/12 ml squared, as long as it's spinning around the middle. Okay, you might want to do this and just jot down that number. How many kilogram meters squared is that? Okay, and hold on to that, and then go through this lab and go through this procedure and see how close it is, and it should be pretty close. Okay, so that's just a side thought there. Okay, but I want to check that. Okay, now let's get to this table. What values measured? So zoom in here. First column, radius in meters. Now notice all the units they gave you guys are classic SI units. We got meters, kilograms, seconds. Okay, so think about that. I mean, if you got some small parts, like if we're talking about a radius of pretty close to a centimeter, then how many meters would that be? Is that 0.01, right? 0.01. Okay, like 0.1 would be 10 centimeters, so 0.01 would be about a centimeter. I don't think this is the exact value, but I think it's pretty close to that. Okay. The mass, okay, the lab mass that's hanging down, how many kilograms is that? Okay, so these numbers have these masses have numbers stamped on. For example, this one has 200 grams stamped in it. So guys, how many kilograms would that be? 0.2, right? So 3 decimal places, so that'd be 0.2 kilograms. Your very largest lab mass goes up to 1 kilogram. Okay, so keep that in mind. All right. Next column. Oh, now here's where maybe I shouldn't have done this for this next column, but we're getting into the part where I split it into 3 parts. Like you take 3 trials and take an average, which is one of the AP steps. You guys know that you're going to get an FRQ in May that involves experimental design, and one of the points that you will get on the exam will be do multiple trials to reduce uncertainty. Okay, so that's what this is about. Like do 3, take an average. Okay, so what's the falling distance in meters? I'll show you guys how it corresponds to this picture. Okay, you say, maybe how far does this lab mass fall? It should be in the ballpark of about 1 meter. Like maybe 0.9 meters, 0.95, maybe 1.1 if you have a pretty good stack of textbooks here and move this up a bit. Right? But it should be kind of in the ballpark of about 1 meter. Okay. How much time does that take in seconds? So you need a stopwatch. Did you guys bring your cell phones today? Ooh, good, because I forgot to tell you guys that detail yesterday. I was hoping you guys would remember your cell phones. So you guys have the stopwatch function. Now, I did also print here, measure. So those are direct measurements. Okay, now this next column is a calculation, and I threw a formula right here. I bet most of you guys are looking at that and know exactly where that's coming from. But this does go back a while. You know what this lab, even though this is a rotational lab, going through this lab, last class I realized that there's actually a lot of good bits of review here, and this is a kinematic motion review. So what is the acceleration of that landmass? Well, based on falling distance and stopwatch time, and it starts from rest, right? So it's home. Isn't that going to feed into this formula? X equals v naught t plus half at squared, right? So how far does it fall as a function of time if it's accelerating? Okay. Oh, but start at rest. Oh, I can simplify this formula if I know it starts from rest. What part gets simplified? Yep, v naught t goes to 0, because v naught would be 0 if it starts from. Okay, so that would just boil down to this. How far it falls, starting from rest, is 1/2 at squared. Okay. Oh, you know what story I remember attaches to this formula? Go to mine shaft. Drop a rock. Takes 5 seconds to hit the ground. I wonder how deep it is. About 125 meters. College. Guys know that? Hey, this is the college equation. Okay. Now, the acceleration in that case was pure free fall. But this landmass is probably going to accelerate down kind of slowly. So it should be a kind of a small number. But see if you can solve for that. Right, well, let's just do a little algebra switcheroo. Okay, cross multiply up to 2, divide down t squared. Wouldn't the acceleration be 2 times the falling distance divided by the time it took to do that squared? Right? You guys see that? You guys hear that? And that is exactly what this says to do right here. It says acceleration is 2x on t squared. And so it's just the college equation, just rearranged. Okay. Next part. So here's the big picture of what's going on. Let me zoom in on just this part right here. Just zoom in on that. Okay, so we're looking at this. Okay. Now, you guys know that well, this pipe is rotating. In fact, it should be speeding up rotating. It has some angular acceleration because there's a torque on it, and the torque is caused by some force, say the tension in the string acting at this radial distance. Would that be true? Okay. Now, is the tension in the string equal to the weight? You guys paying attention here? Because what I'm saying right here, I could totally see being a prime multiple choice question on the AP exam. Okay. Is the tension in the string equal to the weight of this landmass? Let me see show of hands. How many guys say it is? How many guys say no, it's something a little bit different? Yeah, okay, yeah. You guys remember this. It is something a little bit different. Let's go through the review of why it's different and exactly what it is. I'm going to do a free body diagram for that landmass. Free body diagram. This is, of course, something you guys should be able to do by this point. You know what? We've actually gone through 6 of the 7 official topics. I bet a lot of you guys could actually pass the AP exam right now if you took it. And this would be like one thing that you have to do. So let's say we got some mass M. Let's do free body diagram. Guys, how many forces on this landmass? I'm thinking 2 that matter, right? There's the weight acting down and the tension acting up, something like that. Okay. And notice how I did not draw those equal to each other, right? Guys, is this landmass in equilibrium? It is not. There's a net force down, so it's going to accelerate down, because if there's a net force, it has to accelerate, right? Now the acceleration is going to be really small. It's going to accelerate down really slowly, okay? But there's an imbalance. So I can say this net force is equal to the landmass times the acceleration, right? Hey, that's Newton's second law of motion. Net force, wouldn't that be the difference between the weight down and the tension up? Okay, so I got weight down minus tension up equals mass times acceleration. Actually, the process I'm doing right now has shown up, I'm pretty sure several times in past AP FRQs, so got to know this process, right? And let's say you solve for this tension. And remember why you want to solve for this tension. We're honing in on that tension because that tension would be the force at this radial arm that's causing a torque, causing this thing to spin. Okay. Switch this around a bit. Wouldn't tension be equal to mg minus ma? Can that be true? Okay. You could factor out the mass. And oh, does this look kind of familiar? Does it look familiar? It should, because you guys have seen this, right? Remember tension in an elevator cable? It's m times g plus or minus a. Remember that? Right. Now, if you see this on AP, especially the FRQ section, which could totally happen, you would have to derive this from scratch. But that's a good thing to memorize in the back of your mind, is that tension in an elevator cable is g plus or minus a. It'd be plus if it's accelerating upward, but here it's accelerating downward, so it's like it has a little slack in the hip, right? So the tension is actually a little bit less than the lab weight. And that is the next column in the table. It says, zoom in here, tension, M times G minus A, right? Something you guys have seen before. It goes back a few weeks, but right. Right, then the resulting angular acceleration, which actually comes from numbers you have from before too. So take this acceleration calculated. Actually, this calculated linear acceleration feeds into both right here and also right here. Okay? But what's the whole deal with divide by r? Well, remember that yes, okay. The linear acceleration of this down and the angular acceleration of this spinning are related to each other. How are they related? They're related by the radial size of that central pipe. I'm looking at this right here. Okay? So remember how far the lab mass falls and how far that PVC pipe turns is related. Right? How fast it's falling and how fast it's turning is related by, and how fast the lab mass is accelerating down. And the angular acceleration PVC pipe system also related by the radius. Right? So if you know, say, two of these things, you can solve for the third one. And that's exactly what it says to do right here. The angular acceleration in radians per second squared of that PVC pipe system is linear acceleration divided by the radius of that central pipe. Okay? Right. And then finally, get the torque. Well, finally for the table, the last column on the table, right? R cross F, where F is the tension and the strength that you calculated using the tension elevator cable formula. Okay? Guys get that? Okay. Questions so far? Okay. So that's the table. Now pick 5 different lab masses. Again, this is going to take up more than today to finish. You might get like 2 or 3 of these done today. Okay. Then I've got a graph for you guys. And this graph says tau, the torque in Newton meters, versus alpha, angular acceleration in radians per second squared. Now, why would I pick those as the axes? I bet some of you guys know already. Remind you guys a couple formulas about torque. Now, I introduced you guys to torque as R cross F, radial arm crossed with a force. But I also connected torque to this other formula. What's the other formula for torque? I times alpha. Exactly. Remember how this is analogous to F equals ma? It's sort of like Newton's second law of motion in a rotational context, right? Put a torque on something. This is going to cause it to accelerate in a rotational. How much does it accelerate? Angular acceleration? Well, that'd be inversely proportional to how much inertia there is. And that's what you guys need to figure out is what is I? Okay. Hey, does this also look like the form y equals mx? Y equals mx? Okay. Oh, so I bet if you had a graph with the axes like y and x, except it'd be tau and alpha, see what that would look like. So tau in Newton meters and alpha in radians per second squared, then you should get, I'm going to guess what your graph is going to look like. And you guys can do the experiment and tell me how close it is. I bet it's going to look something kind of like that. I bet these points are going to line up in a straight line. Okay. And furthermore, I'm guessing, and I might be wrong about this. You guys can tell me if I'm wrong. But I think that you guys are actually going to get an intercept here, like a y-intercept. Right? Maybe I might call this tau naught. Right? Speaking of like F equals ma, tau equals I times alpha, this is really net tau, isn't it? Okay. So I'm going to draw this way. And this is sort of a side thought, but I'll plant this idea and see if you guys can figure this out. If you guys do get a graph like this, which I think you probably will, what does this intercept represent? And it does represent something physically. That's if you get it. But regardless of whether you get an intercept or not, what does the slope of this line represent? Rotational inertia, because tau equals I times alpha, well, tau net, right? Maybe like a change in tau, right? Tau, right? Something like that. Is that? Questions so far? Okay. So once you get the slope of the graph, that's this box. The unit would be kilogram meter squared. Okay. Don't forget to also do that 5-part lab write-up, okay, because tomorrow I'll take you guys through the scoring rubric and have you guys score yourselves on the 12 points too. Okay. Okay. You guys good to go? So everything you need, back to your lab stations. I'll help you guys out, and this will take probably a couple days.